In our previous video, we saw how to calculate work and heat in an isothermal process. So that's a slow process on a gas in which it's compressed without a change in temperature. Now we'd like to consider another extreme. This was the slow version. What if we compress a gas very quickly? So compared to this initial case where the temperature doesn't change, we're going to compress it very quickly, and because heat cannot flow out of the gas, we'll assume that there's zero heat. That is the other extreme. In this case, we're going to end up with a difference in temperature. We're going to end up at a higher final pressure than we initially had in the isothermal process. This process, because it does not allow heat to pass across the boundary, is called adiabatic. A meaning not, dia means across from Greek. Adiabatic means that heat cannot cross the boundary of the system. So we're assuming Q is equal to 0. Notice the difference between temperature and heat here in the isothermal process. Delta T was 0. Here we have no heat, but the temperature is going to increase as a result. In our discussion here, we're going to use the fact that we've discussed previously, a result from considering the Equipartition Theorem, which is that the internal energy of the gas, I'll call it U here, is equal to F halves, that's the degrees of freedom of the gas divided by 2, times the number of moles, RT. Now remember that the degrees of freedom is the number of ways that we can store energy quadratically in the molecules, and F is equal to 3 for a monatomic gas, or 5 for a diatomic gas. This is because, remember, we bring in those 2 additional degrees of freedom. If I have a molecule shaped like a dumbbell, it can rotate this way, or it can rotate in and out of the screen. So those are 2 additional modes of energy storage that we have for a diatomic molecule. Now, if the change in energy, if the energy is proportional to the temperature in this way, since temperature is a measure of energy per mole or energy per molecule, we know that the change in energy will be F halves nR, the change in temperature. In all these cases, we're considering a fixed number of moles, fixed number of molecules in a sealed cylinder, as we might have in, say, a steam engine. Recall the first law of thermodynamics, which says that the change in energy is equal to the heat plus the work, but here the heat is 0 because we're considering an adiabatic process. So the change in energy is just the work in this case. So I see that the change in energy is F halves nR delta T, but I also know that the change in energy is the work. And the work is minus, we know, the pressure dV. Here's a point where we have to be careful. I know that I'm considering a small change in energy caused by a small change in volume. We're going to assume that this process happens quickly enough that heat can't escape, but slowly enough that we can break this into steps where the gas is in equilibrium the whole time, meaning I haven't set up any sound waves in the gas. That would complicate matters. This approximation that the gas is compressed fast enough to have no heat, but slow enough to not set up waves, is called a quasi-static process. So we have 2 expressions for the change in energy of the gas here. F halves nR delta T must equal negative P dt dV. So I have a relationship between changes in temperature dt and changes in volume dV. Notice I've pulled a little bit of a fast one here. I'm talking about deltas and d's here. We should be consistent. P delta V, delta U is minus P delta V, and F halves nR dt, this d change that I'm making from delta is just to indicate that these are infinitesimal changes throughout a process. Now we can again invoke our old friend, the ideal gas law, PV equals nRT, to get a relationship between P and V here. So P, remember, dividing both sides by V is nRT over V. This gives us the relationship F halves nR dt equals minus nRT times dV over V. Notice we've got an nR on both sides, so this will cancel out. And I see some nice symmetry here. F halves dt over T is equal to minus dV over V. Now, I don't really like seeing these differentials hanging out without any clothing on. I'm thinking that they need to be wearing one of these guys. So anytime I see a dV over V or a dt over T, I'm thinking probably that I need to add up the change as this process occurs. What is happening in each of these cases? Well, these processes happen over time, and each volume corresponds to a temperature at that volume. Temperature will be changing as a function of volume now. So we're going from some initial volume to some final volume, and some initial temperature at that initial volume to some final temperature at that final volume. So these bounds match each other over the course of the process. Those values correspond to each other. Now remember, this is one of our more basic integrals. Integrating dt over t gives us a natural log of t. So we're going to have an f halves natural log of, remember that the difference of logs between the upper bound and lower bound is equal to the log of the ratio between the upper bound and lower bound. So natural log of tf over t initial will equal minus the natural log, same form for the integrand here, v final over v initial. This is a case where we can exploit some log laws, so I know that a constant times natural log of a ratio, I could take this f halves and make it the exponent of the logand, the thing that I'm taking the natural log of. So that would simplify things a little bit. Natural log of tf over ti to the f halves power. And here I have a negative natural log of v final over v initial. We could simplify that a bit by noting that negative of a natural log is equal to the natural log of the reciprocal of that fraction. So rather than v final over v initial, we'll have v initial over v final. So we have two quantities whose natural logs are equal. We can clear these natural logs by exponentiating, take e to both sides, and that shows me that t final over t initial, all to the f over 2, is equal to v initial over v final. Moving finals and initials both to the same side of the equation, this shows us that v initial times t initial to the f over 2 is equal to v final times t final to the f over 2, where f, remember, is the degrees of freedom for the gas type that we're considering. So I see this combination, v t to the f over 2, is a constant. So at every point in this process, v times t to the f over 2 equals a constant, the same way that p times v was a constant in the isothermal process. So this is the characteristic of adiabatic compression.